In the previous two episodes, we talked about some basic concepts, the types of reagents and the types of reactions. For the current presentation, we take up the types of organic reactions, which include substitution, addition, elimination, rearrangement, oxidation and reduction. We shall deal with these reactions in some details with examples for each of the types. And also we plan to take up some of the reactive intermediates like carbocations, carbanions, arynes, free radicals, carbenes and nitranes. The first type of organic reactions are called as substitution reactions. Substitution reactions are one type of reactions which the organic substrates undergo, and as the name suggests, here the substitution of an atom or a group by another atom or a group takes place. For example, reaction of methyl chloride with sodium hydroxide. Here the chloro group of the methyl chloride gets substituted by the hydroxy group, and from methyl chloride we get methanol as the product. So, this is an example of a substitution reaction, and the substitution reactions are generally shown by saturated hydrocarbons like alkanes, haloalkanes and alcohols. But besides the saturated hydrocarbons, substitution reactions are observed in unsaturated aromatic compounds also, like benzene and its homologues. The other type of reactions are addition reactions. In addition reactions, two molecules combine to form one molecule. For example, addition of bromine to ethylene, as shown in this reaction, BR-BR adds to the double bond and forms a dibromo compound. In fact, this type of reaction is a detection reaction for alkenes. And as said, this is a characteristic of compounds with multiple bonds. The addition of different molecules can take place to double bond as well as triple bonds. The addition reactions can be classified into free radical, nucleophilic or electrophilic, depending upon whether the reacting species are free radicals or a nucleophile is participating or an electrophile is participating in the reaction. Then we have elimination reactions, and here obviously that the reaction leads to elimination of two atoms or groups from a molecule, and these reactions are opposite to addition reactions in the sense that in addition reactions we have addition of a molecule and here we are losing the molecule. This leads to the formation of double or triple bonds. Again, this is a reverse case of the addition reactions, wherein the addition takes place to a double or a triple bond and leads to a saturated compound, and here we are getting formation of a double or a triple bond. The atoms or groups lost may be attached to same atom or different atoms of the molecule. For example, dehydrobromination in alkyl halides, where the HBr molecule gets eliminated from the same molecule, and the elimination can take place from two moieties also, then also we call it an elimination reaction. Rearrangement of reactions is actually the reorganization of the constituent parts in a molecule. These reactions are also very important organic reactions which lead to the formation of various types of products from the same molecule or from two different molecules also. For example, rearrangement of an alkene into another isomer is the rearrangement within the molecule, wherein we have one isomer of this alkene getting into the other one by means of rearrangement. The atom or groups migrate within the molecule to form the product. Lastly, we have oxidation and reduction reactions. Oxidation is defined as either the addition of oxygen atom to the molecule which is getting oxidized, or alternatively we define it by the removal of hydrogen. For example, combustion of alkanes to carbon dioxide and water as is depicted in this reaction. And also there are a number of organic reactions wherein the functional group also changes. So, depending upon which functional group is getting converted to which one, we categorize the reaction as oxidation or reduction. The groups are arranged in an increasing oxidation state by which the reaction is categorized. For example, in this case alcohol gets converted to ketone, and in ketone the carbon is in the oxidized state as compared to alcohol. We call this reaction as oxidation reaction. Similarly, reductions involve addition of hydrogen or removal of oxygen, which is of course the reverse of oxidation, and in any reaction simultaneously the moiety which is getting oxidized is the reducing agent and vice versa. For example, reduction of carboxylic acid to aldehyde and alkenes to alkanes. So, carboxylic acid gets reduced to aldehyde and alkenes get reduced to alkanes. You can see that there is addition of hydrogen, whereas in case of carboxylic acid getting converted to aldehyde, we have removal of oxygen. So, the example of either removal of oxygen or addition of hydrogen, both of these lead to the reduction reactions. And as you would see in the future episodes, the change in the oxidation state of carbon during an oxidation or reduction reaction actually decides whether the reaction is undergoing an oxidation or a reduction. So, this is broadly what and how many types of organic reactions we have. And you should remember that we talked in our previous episodes about the reaction mechanism. Reaction mechanism is actually the organization of organic reactions in a sequence of steps. The reactions do not undergo in one go. There may be some compound which gets formed in between during the course of reaction while it proceeds from reaction to the product. Such compounds which are formed in between the reaction and the product are called as intermediates. There are some of the reactive intermediates we would deal in the lecture: carbocations, carbanions, arynes, free radicals, carbenes and nitrines. And these intermediates are very important, the reason being that they are highly reactive. As a result, immediately after the formation of these intermediates, we get the formation of products. We start with the first intermediate, carbocations. Here you would recall the first episode of this lecture series wherein we talked about the formation of carbocations by means of heterolytic cleavage. So, carbocations are produced as a result of heterolytic cleavage and they are called Lewis acids, like we have an example of aluminum chloride as a Lewis acid. And the carbocations are obviously highly electron deficient, so they keep looking for an electron rich center and are also positively charged species. They are supposed to be very short lived and therefore are highly reactive. If we look into the structure of carbocations, we will find that there are three R groups attached to the positively charged carbon. It has sp2 hybridization and therefore has a planar geometry. It is very important to talk about the stability of carbocations because the ease of formation of product will depend upon how stable the carbocation is. And the stability of carbocations is again decided by a number of factors which include the inductive effect, the resonance and the hyperconjugation. In the previous episodes we talked about inductive effect. We would like to just have a recall of the facts with inductive effect. Inductive effect is the introduction of polarity in a bond. It operates through sigma bonds, is a permanent effect. So, let us look into the tertiary, secondary and primary carbocations. We know that a tertiary carbocation will have 3 alkyl groups attached to the carbon. The secondary will have 2 alkyl groups and a hydrogen, whereas a primary will have only 1 alkyl group attached to the C plus, and of course, this is a methyl carbocation. The stability of carbocations will depend upon the number of alkyl groups. We are aware that the alkyl groups are electron donating, that is, these have a plus I effect. What will that mean is they will be trying to donate electrons to this C plus ion. As a result, they would be sharing this positive charge. So, if they are able to share this positive charge, ease this carbon by sharing the positive charge will make this carbocation more stable. And if we compare it to a secondary carbocation, we have only 2 alkyl groups which are able to share this positive charge, and primary has only 1, and the methyl carbocation does not have any. Obviously, the stability of carbocation will be tertiary more stable than secondary, it will be more stable than primary, and the methyl carbocation remains the least stable. Resonance is another factor which would affect the stability of carbocations. Here again we would recall what we did in our first episode, what exactly we mean by resonance. Resonance is also called a mesomeric effect, and it is actually the delocalization of pi electrons. We took the example earlier also of butadiene. The delocalization, as was said earlier also, may involve lone pair of electrons, as in the case of this ethylene chloride, where in this lone pair on chlorine participates in delocalization and we have a resonating structure. Therefore, on the basis of resonance also we can say that allyl carbocation is stabilized by resonance. This is the allyl carbocation where double bond participates and tries to ease this carbocation of the positive charge, and because of the shift of this double bond gets positively charged and shows resonance. The structure in general can be represented where delta plus is on both the carbon which are terminal methylene groups, and we say that the allyl carbocation is highly stable. Similar is the case of benzyl cation, wherein the double bonds of the aromatic ring, which are otherwise supposed to be highly stabilized and which are not supposed to be disturbing its aromatic structure, contribute to the delocalization of electrons, share this positive charge in the whole ring by means of the resonating structures which are shown here, and we say that benzyl cation is highly stabilized as a result of resonance. The carbocations are also stabilized by another factor called hyperconjugation. This is a kind of resonance, but this is extended to sigma bonds, and where the pi bonds or a p orbital can be involved. Therefore, it is a delocalization involving sigma bonds through sigma pi or sigma p overlap. The p orbitals in case of sigma p overlap may be filled or vacant also. If we look into the orbital diagram of a sigma pi overlap, we would see that the sigma orbitals can interact with the pi bond which is formed in between this C and this C. So, here though there will not be any bond formed, but still this will be augmenting to stabilize the carbocation which will be formed. If we look into the resonating structures of this, we will find that the hydrogen atom which is contributing to the resonance of this particular molecule with a pi bond does not have a bond in between. Therefore, we call it as no bond resonance. The bond between carbon and hydrogen does not exist in the contributing structures, and the way one hydrogen contributes to this structure, all the three hydrogens would do, and the number of resonating structures can be written. Similarly, the ethyl carbocation has resonating structures which can be written the way we wrote for a molecule which has pi bond. Here we have a ethyl carbocation which has again 3 protons to contribute to the resonating structures with the help of a no bond resonance. And though it is out of context, but it is good information to tell you that ethyl radical gets stabilized by the same means. So, it also by means of hyperconjugation or a no bond resonance gets stabilized by means of drawing a number of resonance structures. And if we look into the orbital diagram of ethyl carbocation, we would notice that 3 CH sigma bonds are there which are able to overlap with the vacant p orbital. So, this is though a weak overlap, but still the sigma bond is able to contribute to the stabilization of the carbocation which is there in the case of ethyl carbocation. Thus, we can say that the tertiary carbocation by means of hyperconjugation again will be more stable than a secondary than a primary, which is again more stable than a primary methyl carbocation. You can see that in case of tertiary we have 3 carbon atoms which are attached to 3 hydrogen atoms each. So, we have 3 plus 3 plus 3, 9 hydrogen atoms to contribute to the resonance structures. Obviously, it will make carbocations stable. So, hyperconjugation also plays an important role in the stabilization of carbocations. The other type of intermediate, that is carbanions. When carbon atom retains the shared pair of electrons during heterolysis, we get carbanions. You will again recall our first episode where we talked about heterolytic cleavage of bonds, wherein carbanions were generated when the shared pair totally went to one of the atoms of a molecule. These are called as Lewis bases also, and because the shared pair goes to that atom, so they are electron rich and would be seeking a positive center for attacking. Carbanions are very strong bases and therefore are very poor leaving groups. What exactly we mean by this is that carbanions are very strong bases. That means they are the ones who can donate their electron pair very easily, and it is very difficult because they have an electron pair with them. It becomes very difficult to detach them from the parent molecule, we have this carbon ion which is drawn here with an electron pair and a negative charge. Because we have 3 groups attached to this carbon, it is sp3 hybridized and has a pyramidal geometry. Besides these types of carbon ions, we have organolithium and organomagnesium compounds which act as carb anions. As you can see here, ethyl magnesium bromide is, we can write ethyl magnesium bromide like this also. You know that magnesium is electropositive. So, a positive charge on magnesium and CH2 becomes partially negative. So, this ethyl group acts as a carb anion and magnesium bromide as the positive part of it. You must have noticed these reactions while studying the Wittig reagents and other reactions. The stability of carb anions also depends on a number of factors. Because they are negatively charged, therefore, these are destabilized by alkyl groups. You can understand, because the alkyl groups are electron donating. So, instead of sharing the negative charge, they would all load this carbon atom with the pre-existing negative charge. As a result, the molecule would get destabilized, and as would be expected, the stability of carbon ions will be just the reverse of the stability of carbocations if we consider primary, secondary, tertiary carbon ions as compared to their carbocation counterparts. And in this case, just the reverse of carbocations, we have the methyl anion as the most stable, because it has only 3 protons attached here. There is no group which will be electron pushing or which will have a plus I effect. Similar to the carbocations, carbanions are also stabilized by resonance and inductive effects by the same way we did for carbocations. We come on to another types of intermediates which are called as carbenes. Carbenes are another type of intermediates which are neutral, divalent with a sextet in the outer orbital. That means their octet is not complete. There is no formal charge on the species, but availability of a lone pair makes it very reactive. And carbenes have the general structure R2C. Methylene, being the simplest carbene, is generated by heating diazomethane CH2N2. There are 2 types of carbenes, because there is a lone pair in the outermost orbital. They have one pair of electrons which is arranged in 2 ways in the orbitals. Triplet carbenes have 2 unpaired electrons, one in each of the sp2 and a p orbital, while singlet carbene have a pair of electrons in a non-bonding sp2 orbital and have an empty p orbital. As can be seen here, this is a triplet carbene and this is a singlet carbene which is paired, whereas the triplet carbene has 2 electrons which are not paired. Generally, carbenes are more stable as triplets. Energy is gained by bringing the electron in the p orbital down into the sp2 orbital, which is insufficient to overcome the repulsion that exists between 2 electrons in a single orbital. So, the triplet carbene is more stable because there is no repulsion between the 2 electrons which do not have the spins to repel each other, whereas in case of singlet carbenes the spins repel, therefore this is not very stable. Nitrines are another type of intermediates which are the nitrogen analogues of carbenes and are neutral species like carbenes. in which the nitrogen atom has only a sextet of valence electrons. The nitrene has 2 bonds fewer than a normal amine and has 2 lone pairs, making 6 electrons in all. These are also highly electron deficient and therefore very reactive. The parent species NH is known as imidogen or azine or imine. Another type of intermediates observed in aromatic compounds are benzynes. Benzene has a triple bond between 2 adjacent carbon atoms of benzene as shown in this structure. The triple bond in benzynes makes the ring very strained because of the disturbance of the alternate double and single bond structure of a benzene molecule. And the benzene is produced during a nucleophilic substitution reaction in the presence of a very strong base such as NH2. You will be reading about this when we study the aromatic substitution reactions. For example, the reaction of chlorobenzene in presence of an amide gives rise to benzene and then the further products. Here is the benzyne intermediate which is involved. The last types of intermediates which we would deal in this presentation are free radicals. You would again recall the free radicals are produced as a result of homolytic cleavage. These are reactive short-lived intermediates with 1 or more unpaired electrons, and this is observed also in NO, NO2, sodium or the chlorine atom. The examples are shown here, and here is the way the radicals are produced. So, in this particular episode of the lecture series in organic reactions, we talked about the type of reactions which the organic molecules undergo, wherein we covered the substitution, addition, elimination, rearrangement, oxidation and reduction reactions. After that, we talked about very important species which are involved in the study of reaction mechanism of organic reactions. We call these as intermediates. We talked about the intermediates carbocations, carbanions, benzynes, carbenes, nitrines and free radicals. All these intermediates will be used and will be talked about when we talk about the different types of organic reactions of involving different functional groups. Thank you.